Welcome to 1007 ICT, 1807 ICT, and 7611 ICT Computer Systems and Networks. This is Lecture 7, Operating Systems. Last time we talked about the idea of addressing, endianness, primary memory, secondary memory, and then we spent a section on data errors, things that go wrong when we're reading or writing or sending information across a network. This time we're going to be looking at the operating system, and firstly the history of operating systems. Then we'll talk about some concepts related to operating systems like bootstrapping, the idea of a kernel, the process that's running at all times, process management, CPU scheduling, dispatching, memory management, and virtualization. So there's a whole bunch of stuff that we're going to talk about. We're going to look at them at a fairly high level. We're just going to introduce the concepts, and these are the kinds of things that your operating system on your device is going to have to deal with, at least in modern computers. So most of the learning objectives will be learning about or understanding this, which means that there's not a lot of process, it's a lot of theoretical background, and so later on we may do some process-based stuff around this, but at the moment it's just getting a sense of how this stuff actually relates to the modern computer. So the biggest and fastest computer in the world is of no use if it cannot efficiently provide beneficial services to its users. Okay, so this example is if you've got a phone and, for example, you tried to update your phone and the update didn't work and you've now got a brick, right? You've bricked your phone. Can you use the phone? No, you can pretty much just throw it out because it's unusable in its current state. Now it may be fixable, right? But you can't use it without the operating system. So it's a useless piece of technology without that operating system. So the operating system is really important. So an operating system, or an OS, allows users to load and run different application programs and to effectively use the underlying computer hardware. So it has to do it in a way that's efficient, perhaps for the user, at least that's what we would like, but perhaps also for the technology that you're working on. So if you've got a multi-user computer, perhaps there are some things that operating system does that are not in your interest, but that are in the interest of keeping the work of other people safe from each other. Okay. So the operating system is the glue that holds everything together, and without an operating system, users would need to physically load the computer with what program it was to run on power up and then reboot it to end the program, which some of the older computers used to have to do. So for example, if you go back to computers like the Commodore 64 or that kind of era, every time you run a program, typically if it's a game, for example, you would have to restart the computer to load the next program. So basic idea here is that the operating system provides the platform or the environment for you or a user to do some work. Right? Okay. Here is an example of a computer. This computer, the way you interact with it, you see the switches on the front? Right? If you want to put information into it, you flick those switches and they represent ones and zeros and you can program it. Does that sound like fun? It's pretty cool, but it's probably very tedious, and probably we are familiar now with environments where we can actually type text and all those kinds of things, so it makes it a lot easier for us to work with. But these are real machines, right? So we've come a long way from that kind of environment. So in terms of the history of operating systems, the first computers were programmed in machine code by using switches on a front panel to indicate ones and zeros. That's the picture I just showed you there. So that's, like I said, it's very time consuming, laborious, easy to make mistakes. You have to have a good idea about what part of the program you're up to, right? So we've made some improvements on that front. In the 50s, data was entered using punch cards or paper tape. What that meant was if you've got these cards, you can now group jobs together. So if you've got a job that does a particular kind of thing, then you get other jobs that do the similar kind of thing and you can group them together. And you can batch them. So basically you can do batches of jobs. They all do the similar kind of thing in sequence, but using the same program. In the 60s, the need to allow several users to access the computer at the same time via some online terminals led to the development of a time-sharing operating system. It's not so popular these days, but you may remember time-sharing apartments, right? So a time-shared apartment is where there's an apartment and, I don't know, multiple people buy a stake in the apartment and they get to use it for 4 weeks of the year. Right? So you just share it across the year. Similar kind of idea. So time sharing is you're sharing the processing power. So later, the need to be able to run several jobs at the same time led to the creation of multitasking, doing things at the same time. Now, I'll say apparently at the same time because with those old processors, you could only do a single thing at a time. but you could switch between them very quickly, and it would look like you're doing multiple things at the same time, even though you're actually only processing a single job at a time, just switching between them very quickly. So the operating system, if you have multiple jobs running at the same time, someone has to look after those jobs. It's not you, it's the operating system. So operating system is responsible for sequencing those, and it also has to allocate and deallocate resources as required. So in the 70s, the need for microcomputers to support file systems led to the development of the disk or DOS-based systems. So just think about that in the 70s. Were there computers before the 70s? Yes? DOS, or the disk operating system, came out in the 70s. What were they using before? Some other environments, right? So DOS was an improvement over those previous environments. Okay, you're probably familiar with DOS, and compared to, at least the graphical user interface, the DOS environment is not as nice to use for most people as the graphical environment. Does that also make sense? Right, it's powerful certainly, but it's nice and easy to be able to click on the screen or double click something to open it, for example. And has some limitations though. So in the 80s, Xerox invented the graphical user interface. So that was another improvement. Before it was all text-based. Later, distributed operating systems were developed for computers that could run tasks on several interconnected processors. So now not only are we working on a single computer, we're working across computers and across some kind of network. And so in the 80s, these evolved into network operating systems, which makes other computers on the network appear as an extension of your computer. And a simple example of this, you probably have experienced this in the labs. Right, when you log onto your computer, you have an S number drive or an H drive or a G drive or some kind of drive that follows you around. Yeah, so if you log into this machine, it'll show up on this machine. If you go to a different lab, you log into that lab, it'll show up on that machine. Is that drive actually on that computer? No. It's mapped somehow to the computer that you're at this point in time. So it follows you around in a sense. So it's accessed across a network. It becomes available when you log in. So a real-time operating system is used in embedded computers for controlling advanced electronic or mechanical processes. So some example devices with this. So most of their operating systems that we deal with are not real-time. Right? They try to be as effective as possible. For example, when you're streaming something, is it important that the processor or the computer that you're using spends most of its time trying to stream the information? Yeah, otherwise you get lag, and the stream will stutter or it won't update quickly enough. But it's not a real-time system. A real-time system is a system where it will absolutely guarantee that you will do this particular operation in this particular time frame. So that's really important for things like the self-driving cars. You can imagine if the self-driving car, it's running an operating system and it's driving along, and all of a sudden it has to do an update. Would that be okay? What do you think? In the middle of its driving around? It's probably not good for the pedestrians, right? So there are some requirements on these real-time systems where if you say you're going to do something in a period of time, you will guarantee that you will meet that. And that might mean that they don't have things like hard drives. Right? They might have different kind of storage devices which have a better throughput. Here is a picture of, on the left, some punch cards, and there on the right is a tower of punch cards. Can you imagine if you knocked that tower over? Right, you would have a lot of time trying to put that back together. And so you can see some of the limitations with writing programs using this technology, right? Just in terms of space, in terms of, do you think reading punch cards is slower than reading stuff from a hard drive? Yes, it's a physical, be a lot slower. So again, there were improvements were made in terms of storage. We talked about some of those already as well. So in terms of an operating system, it generally consists of something called a memory resident kernel, which means it's always there, and then some other memory non-resident system programs which can be arranged logically as some layers. So if you're looking at the bottom, we'll start at the bottom of that diagram on the left. There's the computer hardware. So these are the chips, right? That's the ones inside the computer. Now above that is where. So the first thing on the left is the kernel. That's this memory resident program that's always there. You can think of that as a little program that just sits there in a loop and that just does the things that need to happen for this computer. You see next to it are the device drivers. And so because you can plug in different devices into your computer hardware, you need something to translate between the instructions that you want and the instructions that it accepts. So for example, inside your operating system, inside Microsoft Word somewhere, right, like in your program, you might have a print button. So if you print something, that gets translated into something which talks to the printer somehow and generates a page of text or diagrams or whatever. There's a lot of work that goes into that translation, but something has to be able to talk to that device because every printer is different. Does that also make sense? Okay. So that's the kernel and the device drivers, really low down. Above that is a service layer, and service layer is a layer that has a set of functions or an API. You may have seen that, an application programmer interface, which is something, it's basically a collection of functions or things that you can do at that particular layer, and you can ask the machine to do those particular things. And it might be something like print, it might be read from a file, write to a file, close a file, those kinds of things. And so that service layer contains a set of functions which are called by the application programs, which are things like Microsoft Word or your chat program or anything like that, and they load, manage, and execute programs. Right. So if you are a program, and you'll see the top level is the user. Below the user, you'll see there's user applications and the command layer. The user applications, if they want something done like printing something, they will need to talk to the service layer and say, I want to print something. The service layer will work out, okay, you want to print something, I know how to do that, I'll tell the rest of the environment how to do that for you. Right? I'll take that command and implement it. So that's the user applications. To the left of the user applications is the command layer. And so this could be a DOS window, right, or a Unix environment where you type stuff in, or it could be you double clicking on something. Does that also make sense? So there's different ways you can implement the command layer. And the command layer is basically the thing that accepts commands from you, right? So however that's implemented, it doesn't really matter, but there is some need for one of those sections. So when we start up an operating system, it doesn't just start up by itself, right? So particularly with modern computers, you can load different operating systems onto your computer. So for example, I've got a Mac and I'm running Windows on it. Right? That's possible because I can switch out the operating system in some way. If I couldn't do that, I would not be able to have a different operating system on this particular hardware. And so there's this process called bootstrapping, and the execution begins with something called the bootstrap loader. It has a number of different names depending on who you talk to, but we'll call it the bootstrap loader. It's stored in the BIOS or the ROM. Remember, ROM was the thing that you can't change typically. It looks for the operating system program in a fixed location. It loads it into RAM. Now, it doesn't load the whole operating system. How big is Windows these days? It's huge, right? Gigabytes of stuff. So it can't possibly load the whole thing. It loads a little bit of it, enough so that the rest of it can be loaded. It then transfers control to the starting location of the operating system, and then the loader program in the operating system is used to load and execute the user programs and all the other things that you need to actually get the environment up and running. So bootstrapping, there's this idea between cold and warm boot. I probably don't have too much to do with that these days, but a warm boot, basically you don't have to restart and retest everything part of the system. It's already on, whereas the cold boot, you start up from scratch and you test the memory, and you might see that when you start the computer up. So let's have a look at the first diagram. So in the ROM or the BIOS, when the computer is started, the program counter points to a fixed address in the BIOS where the bootstrap loader routine lives. So somewhere, program counter, yep, pointing into here, and that thing says go to the disk, read this block, and load it into memory. When you get there, start it executing from the start and go through the steps that you need to go through. So does it matter which operating system is in this box? Well, it must be designed for the computer, but as long as it's designed for this environment, you can switch out the operating system, right? You can pick a different one depending on what you put in that particular section. The kernel, we already talked about it. So at startup, the operating system kernel, the thing that's there all the time and running, is loaded into RAM by a program called the bootstrap loader. It runs continually while the computer's powered up. You can think of it like a loop. Again, remember the fetch, decode, execute cycle loop we saw? Just goes over and over again. Similar kind of thing. It has to be there doing stuff all the time, and it will do them in a particular sequence, right? It contains essential services required by other parts of the operating system and applications. So it's the thing that works out, okay, you just double clicked on this. You need to open up a program. That means I need to allocate memory. I need to do these things, and there's a bunch of things that we'll have to organize to make that program run. So at the core of the operating system, the kernel performs a bunch of things. Here is a list of them. CPU management, scheduling, interrupt handling. We talked about interrupts previously. We'll see them again, I think, in a bit. Process management, so multi-threading, inter-process communication, synchronization, making sure that the things talk to each other and work together harmoniously. Memory management, I need to allocate and deallocate, and sometimes I need to swap the memory from the hard drive to the memory and back again. User management, may have different users on the machine, so access control, login, security, make sure I protect you from them or them from you. I/O device management, okay, what can I access, what can I do? Some things I can access sometimes and not other times. File system management and secondary storage. Mostly what people tend to interact with is the programs in the file system, right? When you work with, say, Windows, you typically just interact with the file system. Does that make sense too? That's the view that you see when you're working with the information. Okay, and so you need to be able to access the files and work with them effectively. So we'll go through some of these in a bit of detail. So process management. A process is a unit of executing software that's managed independently by the operating system. It's a chunk of stuff that does work. And you can have multiple chunks of stuff. Now you can have a program like, I don't know, Chrome, and you can run it, and it could be one process. Now Chrome does multiple things, so maybe it's multiple processes, or even inside the processes, maybe there are multiple things it's doing at the same time. So most programs run as single processes. However, multi-threaded programs run as multiple processes, and there may be multiple threads of control within a particular process. So there's different models here. So I'll just show you, just as a quick example, single-threaded process. There's a program counter, and it updates and it goes through my program, and it might, go back and do a loop, for example, and work like this. But there is only one program counter for this process. However, if I have a multi-threaded program, I might have program counter 1, program counter 2, program counter 3. There are 3 program counters, and they all work independently at the same sort of time. Now, obviously, they can't all run at the same time. The computer might switch between them, right? But in this single process, there are multiple things happening at the same time. Okay. Now, that may be necessary for something like Chrome. So if you're in Chrome, right, and you start a web page, yeah, and you're loading it takes a while to load. Can you hit that X button, stop? Can you stop it from loading? Yeah. Can you imagine that if it's a single process and the program is busy loading, do you think you can interrupt it? No, it's busy. You have to wait until it's no longer busy. So if you want to interrupt it, there must be another process or another program counter or something that's checking for you to tell it to stop. Does that make sense? All right, so it may be a little bit more complicated under the hood than what you're thinking when you just see this program. But if you've got multiple things happening at the same time, you probably need multiple threads or multiple processes dealing with that stuff. And this is one way to implement something like that. So a process can request and receive hardware resources and operating system services. Okay, so if you want memory, you can ask for it. Now the computer might say, look, we haven't got enough memory, you can't have it. In that scenario, either the program crashes or maybe it doesn't do the thing that it was about to do and it tells you I couldn't do that thing, right? So there's 2 different outcomes there. Process management is the core of the operating system services. Basically, you're running programs, they're processes, you have to manage those things. The operating system creates processes, schedules their access to resources, deletes processes, deallocates resources that were allocated during process execution, and cleans things up as you go through. Operating system monitors the activities of each process to avoid problems with synchronization, and the synchronization problems happen because we're sharing resources, right? So we may be sharing a file, and if we're sharing a file, then we can't both write to the file at the same time. One of us will have to wait, right? So we have to synchronize based on that. The operating system also provides inter-process communication, or IPC services, to allow processes to communicate. So if Chrome has 3 processes, maybe they need to communicate with each other. One of the Chrome processes is saying, okay, download this page. I'm busy while I'm doing that. Another process might say, I'm waiting for the user to press this X button. And if they press the X button, I'll tell the process that's doing the downloading to stop. Yeah? So they may need to talk to each other. Single process versus multitasking. So a single process, in some operating systems, you can only have one user program executing at a time. Now, you might have had that experience with MS-DOS, for example. When you type in a command and you hit enter, it finishes the command before you can do more stuff. Does that make sense too? Have you had that experience? If not, you can try that out, but you can run one thing at a time. Now, you can run stuff in the background as well, but that's a different issue. But typically, you can run one thing at a time. But you can have multiple programs in memory. Only one of them can be executing, though. So when the program is finished, then the control is transferred back to the environment. So you type in your DOS command, hit enter, it does the command, and when it's finished, you get the DOS command prompt back. So now you can do more stuff. So when an application program begins executing, the operating system grants it exclusive rights to the whole machine, all of the resources. Now in that environment, if I have access to all the resources, we're not sharing, right? So it shouldn't be possible for me to run multiple programs in that model because we'll have problems. Okay, in this model, yes, it's good in the sense that if I'm using the computer, I have the whole thing, so it's good for me as the program, but it's not very good for the throughput or the efficiency of the environment. So the CPU will often be idle while it's waiting for things, and typically it's waiting for input and output. Now we talked about input and output. Input and output, imagine if it's a disk drive. A disk drive is 1,000 times slower than the memory. Right? So if the CPU is running and it has to wait for the disk drive, is it going to wait a long time relatively? What do you think? Yes, it has to wait a very long time compared to how fast it is. So it will often be waiting for input and output. So we can improve on this single process model by having a multitasking model. And so the multitasking model allows multiple programs to be executed concurrently, or at least what seems to be concurrently. So while one program is waiting for the input and output to take place, which still happens, another program could be using the CPU to do something else. Okay, so the CPU typically switches rapidly back and forth between different programs. It uses something called time slicing, and it just says, look, you get a second. Now, a second is a really long time in a computer, but let's say you get a second, and when you finish that second, I'm going to kick you off, and you get another second, and another second, and another second, depending on which program you are. So the process of selecting which program to run at any given instant is called scheduling or dispatching. There's two different parts to that, actually. So as a diagram here, what that looks like is I am program 1. Now I'm executing, and I execute for a while. Now at some point, my execution results in me having to save something somewhere. Or I have to store something in memory or on the drive or whatever, or I have to read something from somewhere. So there's an input-output request. Now that input-output request is me doing something with that input-output device. When I'm doing something with the input-output device, the CPU is empty. It's not doing anything, which means that program 2 could then start executing its code. Yep, because the CPU is empty. While program 1 is doing the I/O request, that finishes here. Once it finishes, it's waiting for the CPU. Now, if the CPU was available here, it would grab it. But if you look at this sequence that we've got here, program 2 was running. Program 2 needs to do an I/O request. So program 3 starts up because program 1 at this point is not yet ready. So program 3 starts executing. And at some point, program 3 is finished. And now program 1 can go again. Can you see that we're sharing the CPU? And we're basically doing a CPU cycle, an input-output cycle. CPU, input-output, CPU, input-output. And that's a basic way that a program will progress. You do some work, and then you save it. You do some work, you do some save it. Okay, so we can alternate programs if we want to. And if we do this fast enough, it looks like the programs are running at the same time. The next diagram is about the different states that a process can be in. So a process can be in 3 states, at least in this diagram. It can be in the ready state, and the ready state means that it's waiting for access to the CPU. So when you create the process, the first thing you do is you put it in this queue of ready things. Right? It's ready to go. It's not running at the moment, but it could be run. There is a blocked state. Okay, what happens to get to the blocked state is when you're ready, at some point you will be scheduled and you will be run on the CPU. So you get to go. You get to do your work. And at some point, once you have either been told that's the end of your work or you have some input-output to do, you will move to an I/O request. And when you're doing an I/O request, you are blocked. You cannot be run on the CPU because you're waiting for something. It doesn't make sense to put you on the CPU because you can't execute any code. Right? So you're in a blocked state. Once you're in a blocked state, you will become unblocked when your input and output is finished. When the input and output is finished, you'll go back to the ready state, and that means you can be chosen to be run on the CPU. So in this ready state, there will be a group of process 1, process 2, process 3, and so on. They're just hanging around in the ready state until they get the chance to go. In the blocked state will be any processes that are still waiting on input and output. So the processes move through these queues until they have finished doing the job that they need to do. Right, now, typically for us, when we're using a Windows environment, it's when we close the program. Right, that's the end of the program. But other environments where you run a command, it runs for a while, then it stops by itself. So it depends on the environment. So in terms of scheduling, you notice that we have a ready queue, and that ready queue has multiple jobs in it, or potentially multiple jobs. If I have multiple jobs, that means I need to be able to choose between them. And I have different strategies for doing that. And the strategies are actually quite important. If I choose badly, my performance is going to be bad. Right? It will be slow. If I choose well, my performance should be better. So there's some strategies here. There's multiple strategies, by the way. These are just 3 of them. The first one is the obvious one. First come, first served. The first one there gets to go first. That seems nice and fair. Right? It's the kind of model we use when we're working at, I don't know, you go to the supermarket. The first person that shows up at the counter gets served first, right? We're all happy with that model? Okay, we're happy with that, I think, as far as it goes in terms of the fairness. But what if there's a person there who buys 10,000 things and you have to wait and you want one thing? Is it still fair? No, you have to wait a very long time for this person to finish their process before you can go, even though you've only got a small thing. So maybe there's a more efficient way to do it. Right? So another one might be explicit priority, and we see this in other environments where someone is more important than someone else. Right? So they're more important, they get to go first. It's not fair, right? But it's maybe more effective or efficient depending on the priority, or depending on the reason for the priority. And in a computing environment, maybe the priority is I'm doing video streaming. So I should get to go first, or more often than other people, because the video streaming is the most important thing going on at the moment. Does that make sense? Okay. The last one there is the shortest remaining time. Now, I'll point out this. Technically, this is not possible, but you can make an approximation. So the shortest remaining time says, okay, every job has so much time that it will spend on the CPU. If I look at how much time it's going to spend on the CPU, if I take the shortest one, I will get the best throughput. It's all the people with one item go first, and the person with 1,000 items goes last. Yep, that's the model we're talking about. Now, it's not really possible in practice because you don't know how long someone will be on the CPU. You can estimate, though, and you can have some algorithms to process that information and get a pretty good estimate. So you can do this fairly well, but it's not technically possible to do it exactly right. Does that also make sense? Because you don't know what each process will do. Okay. So there's 3 different models, and they each have challenges or issues with them. We have the idea of preemptive scheduling and non-preemptive scheduling. So an operating system can run several processes concurrently, but every one of them has to take turns at accessing the CPU. So some operating systems allow each process to decide when they want to let another process access the CPU. That's non-preemptive scheduling. If I leave it up to you when you want to, leave the CPU, that means you have control over the CPU. I can't force you to leave. Is that a good environment, do you think, for a computer? Can you have malicious programs? Programs that, want to take over the computer and not make you able to use it effectively? Yes, you can. So if I have a malicious program and I've got this model and it takes over the CPU, it may never give me back the CPU. Now, it might do it maliciously, it might do it by accident. There may be an infinite loop. Has anyone written an infinite loop here? A loop that just keeps going over and over again? Yeah, some people. If you haven't done it yet, you will do it eventually if you're writing a program. It will happen. Right? So it might not even be intentional. So this is not a very good environment if you have multiple people, multiple jobs, and so on running, right? Because one job can take over the whole machine and not give it back. So a preemptive operating system, in our view, is better because it can interrupt the process and force it to stop. So I can give you the CPU for a bit, and if you take too long, I'll kick you off. And then I'll put someone else on. But I control that as the operating system. Does that make sense? Which is a much more effective environment for getting the jobs done and making sure that they finish. So preemptive scheduling interleaves processes based on something to do with a timer. There must be a timer involved, and that timer counts down until it's finished, and when it's finished, there's an interrupt typically, and it stops the thing on the CPU from running. So interrupts generated by the timer are used to involuntarily remove the running process from the running state. The process has no choice. It doesn't own the computer, it gets kicked off. The scheduler then dispatches one of the other processes that is in a ready state. It chooses the next one and gets the next one to run for however long the timer is. The input-output requests are also interrupt-driven, so when a process wants to do an input-output function, it generates an interrupt, and that interrupt can trigger that this process starts. So I'm a process running on the CPU. I can be kicked off by the operating system, or I can choose to leave myself, and if I leave myself, then I tell the operating system I'm leaving, you can put someone else on. So both of those cases are okay. So here's an example of time sharing the CPU. So when the timer generates an interrupt, the process scheduler, the thing that chooses the next process, is invoked to handle the interrupt, and the scheduler will then dispatch the next process and then continues and waits to the next timer interrupt. So let's just look at this as a diagram. So program 1 is running. It's executing, it's on the CPU, and it says, okay, your time is up, you get kicked off the CPU. Is there anyone else running at the moment? No, you are the only one running, so it's finished, and you will be waiting for some time. Now, if no one else is in the system, you might get chosen to go again. That's perfectly fine. But if there's someone else, like program 2, the dispatcher is running on the CPU for a little bit, this red thing, right? And it needs the CPU to do some work, so you have to use the CPU for it. And it says, okay, who's next? Okay, I'm gonna choose program 2, and program 2 is going to run for however long the timer goes for. And at this point, the scheduler gets to run again, and it says, okay, who's next to go? Okay, we'll go program 1. So it looks like it's just interleaving them, right? It's just choosing one, then the other one. Now that's a particular model. There might be other choices that you could make there. Maybe program 1 has a higher priority, and you should always choose it first, right? Maybe that's the case. This is an example that shows you it changing between programs based on the timer. Now, one of the things you'll notice here, you see these red bits, the scheduler? The scheduler uses the CPU, right? It has to do some work. What would happen if the scheduler, this red part, is the same length as this executing part? What would happen to the speed of your computer? Would that be a good thing or a bad thing? It's a bad thing. If they're the same length as the timer, you halve the speed of your computer. That means that this red thing, this choosing the next job, should be very quick. Yeah, it should be long enough that you make a good choice, but quick enough that you don't reduce the speed of the machine too much. Does that make sense? It happens a lot, right? Okay. Dispatching. So dispatching is the task of switching between processes. The process's context or volatile portion is the information that defines a process, and it's contained in the CPU's registers. Remember the registers, MAR, MBR, and all those registers? You need to save that information if you're going to switch between jobs. So we just saw that we're going to switch between jobs quite a lot. Every time we do that, we have to save that information. Otherwise, when we come back, we're working with different information, right? And we're not going to get the result that we want. So the operating system saves the process context of the running process, the one that's running right now, to the stack, which is a memory space that we have reserved for this, and it loads the saved context of the next process from the stack. So looking at this again as a diagram, just track through it. We've got process A. Process A is running. It's got some registers that it's using. There's an interrupt. The interrupt says, okay, process A's time is up. Start the scheduler. When I start the scheduler, I need to save the registers of the current process. The current process is process A. On my stack, I've now got the registers for A. Does that make sense? Okay. Select the next process and then restore the registers of the next process. So I've got the registers for the next process, let's say process B stored somewhere else. I'll grab those and load them up. Does that make sense? Okay. And then I start running process B. Eventually process B is kicked off the CPU, there's an interrupt, and the process happens again. Save the registers, right? Choose the next one, load up its registers. And it just happens over and over again. And again, this should be quick, because if it's not, you're wasting a lot of time. You're not doing any processing at this point, you're just setting up the machine to be able to switch between different jobs. So this is called context switching, this idea. You're changing the context from one job to the next job, and to do that you have to load and save registers. In terms of memory management, okay, so manage allocation and freeing of memory used by running processes. That's one of the jobs of memory management, to do that. It's used to protect one process from being corrupted by another process. You may have seen lots of different errors around this. You may have seen segmentation faults, or stack overflows, or there's a whole bunch of different errors that you could get from this if you try and access memory that you don't own, right? So it permits computers with small main stores to execute programs that are far larger than the main store. So what we're saying here is, if I've got a 2 gigabyte computer and Windows is 8 gigabytes, can I run Windows? Well, technically no, right? I don't have enough memory. But do I need to load all of Windows at the same time? No. So maybe I can organize it so that I just load just enough so that I can run it with my 2 gigabytes, and then I can run bigger programs than I actually have space for. It's used by multitasking operating systems to make it look as if each process has the sole control of the CPU. Alright, so that's really important for us. If I'm using the computer and someone else is using it at the same time, I don't want to see their stuff. Does that also make sense? I don't want to be impacted by their stuff if I can avoid it. So here is an example of a Windows error message. So this one is unable to register the DLL OCX load library failed code 998, invalid access to memory location. That's pretty specific. Basically, we tried to access a memory location and we're not allowed to. Has that happened to you before? Yeah, I'm sure it's happened, right? And so it does happen. So the operating system is trapping these things. If it happens, maybe the program is malicious, maybe it's a virus or it's something like that, or maybe it's just a mistake, right? Maybe there's a part of the program that's not working properly, all right? So memory allocation. When a process starts, it is allocated a chunk of memory and the program is loaded into it. When the process ends, that thing is deleted from memory that leaves a hole where it was. A new process will be loaded into the unused memory, but if it's too big to fit into any single block of free memory, it will be fragmented. You maybe have seen, in terms of disks, you can defragment a disk drive. Have you seen that process? Yeah, so when your disk drive fills up and you delete stuff and you fill it up and you delete stuff, eventually you get little bits of space that you can't use effectively anymore. And so you have to defragment your hard drive to make sure that you reclaim those bits of space. Same thing happens with memory. Now with memory, one of the nice things is you can just switch the computer off, right, and start it up again, but that's not really effective if you want to keep using the computer, right? So multitasking systems rapidly run into memory allocation and memory fragmentation issues. So I'll show you just a really simple example. Obviously this is at a gross level, so you can imagine that this happens at a smaller level much more frequently, but you have 500 memory units. You want to add A, so let's say we add A. A is here, it takes up 200, that means I have 300 memory units left. There's 3 memory units. I add B, so A is here, B is here, and B is 250, right? And A was 200. Does it still fit into memory? Yeah, how much do I have left? Just 50? Yep. Now I'm going to remove A, so what I've got is I've got B here, 250, and I've got 200 here and 50 here, and I want to add C with 201. Does it fit in memory? Is there any box in my memory that's big enough to fit C? It can't fit here, that's only 200, and it can't fit here because this is 50. So can I put C into memory? No, I can't. I need contiguous space. Do I have enough memory actually available? Yeah, I've got 250. I should be able to fit it, but I can't because of the way I've added and deleted stuff previously. So one solution would be to defragment this and just put B on this side with 250, and then I've got 250 left. Does that make sense? Yep. It's a similar idea to defragment a hard drive. So you can do similar things. Is this expensive? Yes. Moving all this stuff around is actually expensive. So there's a trade-off there. But if you've run out of space, you may need to do something like this to reclaim that space. Virtual memory. So virtual memory is a process or an approach you can take to make it appear that there's much more physical main memory than actually exists. And it permits the execution of programs that are larger than the physical memory. So what we're going to do is we're going to chop the memory into chunks. We're going to call them frames and pages, or just pages if you want. A page is a predefined chunk of memory. It has a particular size. Let's say it's a kilobyte or 10 kilobytes or 20 kilobytes. It doesn't really matter what the size is, at least from our perspective at the moment. The size will be different depending on the architecture you're talking about, but both physical memory and your programs are chopped up into these page sizes. So virtual memory works by splitting the main memory into these physical pages, and then you have a larger set of logical pages, and the logical pages are from the programs. So if you chop your programs up into these 1 kilobyte chunks, you just have a lot of those chunks. If you have more program space than you have memory, that means you have more of those program pages than you have memory pages. Does that make sense too? All right. But because they're the same size, you can put them into memory at some point. So we'll have a look at the details for this as a diagram in a minute. There's a little bit of text we go through. So in reality, the operating system automatically uses secondary memory to store the data pages that don't fit into the main memory. And then when you need to access something that's not in memory right now, you load it in. Now, if you want to load it in, you have to have space for it. And this is where the same size page idea comes in. If they're the same sizes, you can kick one out and you can put a new one in. If they were different sizes, you couldn't do that very easily. All right, so it's important that they're the same size. The operating system maps logical memory addresses from the virtual memory space into the available physical memory. So from the programs, all the pages we have, we can move them into memory. Maybe not all of them, but some of them. And there's a table that tracks what we're doing. There's also an identifier or a bit that says, is it in memory or not? This is what it kind of looks like, right? So what you'll see on the left is a logical address space. That's a program. It has pages A to J. In the middle is the physical address space. This is the actual memory that I have. So just as a question, can my program fit into the physical memory? Can the thing on the left fit into the thing in the middle? No, not even close. The logical address space for my program has 10 rows. How many rows does my memory have? 0 to 4 is 5 rows. Will it fit? Absolutely not. It's way too big. But you'll notice that I've chopped my logical pages into chunks. And are those chunks the same size in the logical side as the physical side? Do they look the same size? Yes, they are the same size. So you'll see that in the physical address space in the middle, it has in there ADGBH. What do you think those letters refer to? ADGBH. They are the names of the pages on the left that are now actually in memory. Is that all the pages for my program? No, it's some of them, right? Presumably or hopefully the ones I'm using. There's also a table there that says, look, logical page, physical page. And is it present? Is it in memory? So wherever the present bit says 1, that means that that logical page is in the memory. And in the physical page column, it says, where is it in memory? If you're not in memory, you see that yellow box down the bottom? That is an unmapped pages disk, right? So anything that's not in memory, where should it be? We've got to store it somewhere. It's going to have to be on the hard drive or a drive of some kind. This is the swap space, or the space that we use to swap things in and out of memory. So I'll show you a slightly different example of this. So this is the picture. Imagine that I've got my program 1 and my program 2, right? And I've got memory. So my memory has how many pages? How many pages? 4 pages. And they happen to be 4 units each, so 4 bytes each, let's say. Yeah? So I've got 4 pages. How many pages does program 1 have? A to K. I don't really care how many there are actually, but there's a lot of them, right? What about program 2? L to R. Program 1, will it fit into memory? What do you think? No, not even close. So if I want to put program 1 into memory, what I could do is program 1 starts here, right? And program 2 will start here. Okay, so I'm going to grab A and I'm going to put it into memory. I'm going to put it in page 1. Will it fit? Yeah, they're the same size. The pages are the same size. Now, I know that pretty soon I'm going to need page B. So I'm going to also load page B up and put it here. But I don't want this one program to take up all the memory because I'm trying to run 2 programs. So what I'll do is I'll load up this one and put it in memory. And then I'll load up this one and put it in memory there. Now my memory's full. How many programs can I run? How many programs are in memory? 2. So I could potentially run 2 programs as long as I'm not using other pages. So let's say that my program goes through here, okay, A goes through the B, sticks around in B for a while in a loop, and then I want E. Is E in memory? No. So now I've got a problem. I don't have any free memory, and I have to find a victim, someone to kick out and replace. Well, I've already been using A, and it's been a while since I used A, so I'm going to use E. I'll put E in here, right? So E's in there, and A is no longer in memory. Now it will fit because my page size is the same size. Does that make sense too? They fit exactly. This is why it's important to have the same page size. Now, if I've chosen badly and E goes straight back to A, is A now in memory? No, so I need to probably get rid of B, and then next thing I go to B, and you can see there's a lot of swapping happening here. So it's helpful if I have a lot of memory, but it's not necessary. Can you see that as well? Because a program will only typically execute one part of it at a time. As long as you have that part in memory, everything's fine. You can just load in the next one. But it would be very slow. Okay, so this is the idea of virtual memory. Very powerful. It's basically what we're using on our computers at the moment, right, to run more programs or bigger programs than we could technically run at a time. We just save the stuff somewhere and we bring it in when we need it. Moving on to software applications. So software applications are programs that a computer executes to perform some specific task. These are the programs that you use that we're familiar with. This is actually how we view the computer. We view it through the programs or the disk environment or the file system. These programs can be stored in memory as either machine code or source code. Applications stored as machine code have been compiled by a program called a compiler, and that compiler takes high-level code like Java or C or something like that and turns it into something that this computer can understand. If you run that compiler on a different computer with a different architecture, you'll get different code. It'll be for that specific architecture. Okay, and that stuff can be executed directly by this computer, by the operating system. Applications that are stored as source code are not able to be run directly on this computer. Another program has to interpret them, work out what's required, and then tell this environment what it wants. That one will be slower because there's an extra step involved. But it's a little more flexible in some ways, right? You don't have to compile it down to this one. You can move it around. You can move it to a different environment, and the interpreter will just interpret on the other environment as well, right? Okay, so the model down the bottom there, the compiled program execution, looks like the box on the left. The applications on the top talks to the operating system, talks to the CPU. On the right, for the interpreted program, the application doesn't talk to the operating system, it talks to another program, the interpreter, and then the interpreter talks to the operating system, which talks to the CPU. So you can see that the one on the right should be slower because there's an extra step involved, right? But there's some flexibility that you gain, which means there's a trade-off there. In terms of programming languages, well, they've evolved quite a bit since the early machine code or the ones and zeros that we were seeing right at the start. We typically don't program in that level. We start with machine language at the top. It's binary code for a specific CPU. Assembly language, which are mnemonic instructions for a specific CPU, makes it easier for people to work with. Right, so we just use some small text, English-like text, shorthand for that. Then we have the interpreted language like BASIC, JavaScript, Perl, Python, and so on. High-level procedural language, they're largely machine-independent like Fortran, COBOL, Pascal, C. Database languages, SQL, and so on. Prolog and Lisp, which be specialized for expert systems and some non-procedural programming. And then you have the object-oriented programming language like C++, Smalltalk, Java. There's a bunch of these different languages, and they work with the object-oriented model, and there are different models that we can see here. So as you can see, there are many different kinds of languages, but at some point they all have to be translated in some way so that this computer can execute the code. And there's different ways of doing that. We've seen we can compile it, generate it explicitly for this machine, or we can interpret it, generate it halfway. Does that make sense? Virtual machines. You probably have used the virtual machine at some point, even probably fairly recently or frequently. So some languages, Java is one, are designed to run on virtual machines. So some environments are run on virtual machines. So if you're running, for example, like Windows on a Mac, you could run it on a virtual machine, okay, and that separates it from the hardware. programming languages are the same or are similar. So virtual machines are used to simulate one type of computer hardware while running on a different underlying computer hardware. They're similar to interpreters, but they process binary instruction codes instead of high-level source code instructions, and the virtual machine instruction codes are called bytecodes. So if you look at the right there, you'll see our layer that we talked before, the computer hardware at the bottom, the kernel device drivers, the service layer, and then the command layer, the user applications, and the virtual machine is what we've added on the right there. Now the virtual machine is there because our Java program sits on top of the virtual machine. So does that tell you that a Java program is probably slower than a C program that doesn't have this interpreted step? What do you think? Probably, right? Because there's an extra step in the way. The virtual machine takes Java bytecode. So those are not instructions for any particular architecture that we're working with, but they're a generalized architecture that can be translated for a particular architecture. So virtual machines need to compile source code into their specific bytecodes. That's this intermediate language. And the virtual machine code will run slower than the native code or the actual code on the computer, just because there's an extra step in the way. The other thing that you might notice about this diagram is that a Java program will necessarily use more memory because it also has to run the virtual machine at the same time as the program, right? So there's an extra requirement. So in summary for this section, we looked at the history of operating systems, process management, CPU scheduling, and memory management. And next we'll look at computer networks, and that's the end of this section.